не знаю. Dear colleagues,
Oh, sorry, Angelsky.
There is no voice.
Dear colleagues, good morning. We start our first plenary session. My name is Angelsky. I am the chair of this session, and let me give the floor. The first speaker, Professor Mark Dennis, our colleague, our friend. The title of report, Mark Dennis, the Optical Hypersphere and 3D Polarization Skermions. Please, Mark.
Okay, thank you very much, Oleg, and thank you so much to you and all the organizers for all of your work in putting together this conference. This is the 6th time I've attended Correlation Optics Conference over years, and it's always been very exciting, both in terms of science and in terms of events beyond the science. And I'm looking forward to an unusual way of doing correlation optics over the next few days. So I've changed the title a bit, but it's the same sort of idea that I presented. What we're talking about is Skermionic hopfions, whatever they are, and I will try and explain to you what those are. Since I was last at Chernivtsi, I've changed my institution. I'm now at the University of Birmingham in the United Kingdom. And one of the things we're very proud of in the University of Birmingham is that our first professor of physics was John Henry Poynting himself. I remember my first correlation optics conference in a discussion with some of Oleg's translators more than 20 years ago, that whether Poynting vector should be because it points in a direction like a vector. And I had to explain it has this funny spelling in English because it was somebody's name rather than because it's a vector that points in a direction. Anyway, one of the things that we have in Birmingham that is quite an interesting new development is a Centre for Topological Design. And I will just put in a quick pitch because this centre is something that I'm the director, and we're very excited about what we're doing, So we've got lots of different branches, not just optics and photonics, but quantum technology, soft matter, life sciences, 3D printing, mechanical fabrication, and so on. And it's primarily for training PhD students. So if you know anybody who's about to graduate who wants to do a PhD in interdisciplinary applied topology and topological engineering, we're about to start opening our international PhD applications. And if you want more information, please drop me a line. So I should say this work that I'm going to be talking about, I'm just going to be talking about this single piece of work. These are the collaborators. Danica Čujic, my former student, who has just joined industry, but she was at Correlation Optics 2015. These other colleagues on theory, and then the group of Cornelia Denz in Münster in Germany on the experiments. So just a bit of context or background, because this is the first talk, and I'm sure there'll be many different versions of this over the next few days, that what I'm going to be talking about is free space optics of structured light, where we're thinking about the transverse plane of a beam with polarization, but where the state of elliptic polarization changes with position. So this is the XY plane, and you can measure this with, say, Stokes polarimetry. And this field of ellipsis is changing, and the structure we normally think of is organized topologically by the C points, the points of circular polarization, right-handed or left-handed, depending upon the handedness of the C point, and they're separated by a line of linear polarizations. And these are the different sorts of topologies of C points that we talk about. And obviously, this is very familiar to very many people in the audience. And of course, the way we parameterize elliptic polarization is points on the Poincare sphere. There's this sphere that has a theta and a phi, or its Cartesian coordinates S1, S2, S3 for normalized Stokes parameters, and they determine different states of transverse elliptic polarization. Right-handed circular at the North Pole, linear polarizations around the equator, left-handed circular on the South Pole. So obviously, this is something very familiar to very many of us, but this is the setting that I'll be talking about. Also, I'm talking about three-dimensional states of light. So I'm thinking about propagation in the Z direction. So obviously, I have a copy of each of these planes in for each value of Z. And we would think of, say, these points of circular polarization stretching to be lines in 3 dimensions as the value of Z varies. So this is a phase pattern associated with a Laguerre Gaussian beam with an optical vortex, the red line along the axis. Obviously, this is a scalar beam, and the main interest in a scalar beam is the phase, and we don't normally talk about the phase when we're thinking about polarization. We're thinking about the state of elliptic polarization. So that's the sort of context I'll be talking about. And let me jump right in. I talked about this Skermionic Hopfion. This is the structure, the field that we generate in our experiment. So we structured the transverse polarization and phase. So unlike what I showed you on the previous slide, in this beam, we're structuring simultaneously the state of polarization, and now I'm using colors to represent where I am on the Poincare sphere. So transverse polarization and the phase of a paraxial vector beam in free space into what we call a 3D topological particle. And this is coming from ideas in particle physics, where people talk about a particle from a topological basis. So what is, so we call it a Skermionic Hopfion. So what does this mean? You may have come across Skermions in a 2-dimensional context, either in optics or in other areas. So what is the relationship of a 3-dimensional Skermionic Hopfion to 2-di Skermions? What makes these particle-like? on what is the topology and how is that related to the topology that we normally think of when we're talking about singular optics. Those are the things that I'm going to be talking about in the context of this structure that we have the theory and our colleagues did the experiments for. So this is the outline. I'm going to start by explaining the structure of our 3D Skermionic Hopfion beam. I'm giving a little bit of a background about Skermions, where else they come up in physics, and there's a lot of attention in solid state physics right now. Then this intriguing thing that we call the 3D Optical Hypersphere, that sounds very fancy, but actually is something that everybody here will at least have probably thought a tiny little bit about. And then finally, perspective and discussion. But I'll start with the structure of the Skermionic Hopfion beam, that is explaining the structure of this beam that I just showed you. So let's take a little bit of context, because what I'm doing is a little bit different from what I said at the very beginning is standard for our analysis in singular optics. So we're thinking about a structured paraxial beam. So it's just free propagation in 3 dimensions, paraxial, meaning that as Z or Z propagates, say, up the page here, the ellipses are always in the XY plane. And as I said, as we move from plane to plane, we have a different state of elliptic polarization, but the point of a given polarization is going to change from plane to plane. So we can think of joining, say, the state of linear polarization with this angle to the y direction. We can follow that state of polarization as I go from plane to plane to plane. Or similarly, this state of blue, this state of elliptic polarization here, I follow that as plane to plane to plane. So what I said before, when we talk about C lines, lines of circular polarization, we could follow those as well, but actually there is a line for every single state of polarization we can think of, and we can follow all of those from plane to plane to plane. So actually, if we think about our structured light beam in this way, with all of these different states of polarization parameterized by the Poincare sphere, we have this sort of forest, this bundle of lines, what in other areas of physics is called a texture. So we have a texture of these filaments, these threads, each of which corresponds to a different state of polarization. Now you could analyze any structured light beam in this way, but what we're doing with our Skermionic Hopfion is looking at a particular topology that becomes possible when we think of structured light along these lines. So we're not necessarily thinking of right-handed and left-handed circular polarization as special anymore. We can draw lines for any state of polarization. I should say the way that we have this field that we construct experimentally is constructed by a superposition of a structured scalar beam in the right-handed and left-handed component, and that means that we get this complicated structure. And this is a simulation of this beam I was talking about around the beam axis. So as I said, so I'll be calling these lines filaments. And the ensemble of filaments, the collection of filaments, defines a topological texture. And the other thing to say is we're only looking at the polarization state when we draw these lines. But if you think about the polarization ellipse, it has a phase. And so the phase is changing. The phase is varying as I follow along one of these filaments, where what the phase is, say, denoted by this arrow, changes from plane to plane to plane. So then this is looking now at the structure of this field that we created. So this is again the main field we created. The colors, the hues, represent the azimuth on the Poincare sphere, the major axis of the polarization ellipse. And what you can see, this beam structure has got an axial white line, an axial line of circular polarization. So there's our, so actually it's a C line, a line of circular polarization. And then in the focal plane, there's a circle of left-handed circular polarization. And one word that, so it's one of Marat Soskin's favorite sayings coming from Michael Berry was that when we think of structured light, the singularities form the skeleton of the structure. So in this case, we have this white line and this black circle forming a skeleton for the rest of this three-dimensional structure. How does it form a skeleton? Well, there's around this black circle, there's a torus. And on that torus, the value of S3, the ellipticity of the ellipses, is constant, but the azimuth is varying. And on each of these tori, say this torus here, we have constant S3 being 0, linear polarization. So this is a surface of linear polarization, but the different states of linear polarizations corresponding to the different angles of the polarization, each form filaments that follow these paths that you can see here. In fact, a feature of this construction is that every pair of filaments you choose form a little link. This one is a different value of S3. We still have a torus. There's the black circular polarization line and the white circular polarization line as the skeleton. And these two, again, filaments of different elliptic polarization form a link. So this is the structure, very sort of complicated, intricate topological structure that's set up, we call this Skermionic Hopfion. So the polarization filaments are loops lying on tori of fixed ellipticity, fixed S3, but varying azimuth. The constant azimuth lines are these filaments here, and they lie between our filaments, the C lines of right-handed and left-handed circular polarization. So this is a skeleton of a complex topological structure that we call is like a topological particle. This is the experiment, and it's made by a so the spatial light modulator here creates a right-handed and a left-handed circularly polarized beam, which are then superposed. The right-handed beam has a vortex loop in the waist plane, which ends up being the left-handed circular C line. The left-handed field has a vortex up the axis that ends up being the right-handed circularly polarized C line. And when these are superposed, we get this structure here. So that's actually all you need to get this complicated topological structure. So in the waist plane moving out, there's right-handed circular polarization in the middle, and it goes to left-handed circularly polarized on a circle here, and then right-handed circularly polarized further out. And one of the things that's complicated in the experiment here is that Ramon, the main PhD student doing the experiment, had to recover both the phase by interferometry as well as polarization by usual Stokes polarimetry, and that was let's say the hard part of the experiment, as well as actually getting the three-dimensional structure resolution. Okay, so what can we say more? Well, we've said that each almost, okay, so it's not quite a perfect structure. We can't quite go out to infinity, but we can enclose very much of the topology within the visible beam. And so almost every polarization filament of fixed polarization is a loop. We've already seen that. We've already seen also that every pair of loops for any polarizations is linked together. So here I've got, again, this red and this blue. it's linked together. And along each loop, it's a loop, I can follow here, say A, B, C, D, A, B, C, D. You can see the phase around the ellipse varies. In fact, on the loop, the phase also varies through 2 pi. And it's topological. I'm not going to go through the details. Topologically, the phase on the ellipse varies through 2 pi is related to the fact it's linked to this other filament. The fact that they're linked together is what allows the phase to go through a full 2 pi phase change. So, and this is associated with various structures associated with people call Berry phase or Berry Pancharatham phase. But it's a feature of this topology. And we don't normally think about the phase when we're doing the looking at the polarization, but it's an important feature of what we're talking about when we're talking about this thing as a 3-dimensional structure, because what it means is that we're actually thinking in 3-dimensional points in real space, X, Y, Z, but also 3-dimensional parameter space. Let's say the S1, the 2 angles on the Poincare sphere and the phase as well. So now I'm going to talk a little bit about this background to these things, Skermions, which so have a lot of people excited in various different areas of physics, and where we get this idea of topological particle from. So a question that physicists have asked for many years is, what defines a fundamental particle at all? What, atoms, can I break them apart, or what makes an atom something that I couldn't break apart? Obviously we have subatomic structures, but what defines, say, an electron or a quark? And so these are the sorts of properties that people think of fundamental particles should have. It should be localized somehow. It should be quantized, there like electrical charge or various nuclear numbers, and there should be different sorts of particles. So we should be allowed to have more than one sort of fundamental particle. They should be heterogeneous. And one of the first attempted classifications of thinking about what could make different particles different, he was thinking about the periodic table of the elements, was Lord Kelvin, who guessed that maybe there was the origin of matter was topological, and that different atoms in the periodic table were different knots, and he thought they were knotted vortices in the ether, which was, well, unfortunately not true, but this idea of topology and matter started there. And actually Kelvin's suggestion inspired this gentleman, Tony Skerm, who was a professor at the University of Birmingham, to suggest in the 1950s that maybe nuclear particles, so they were thinking about mesons, primarily mesons and baryons, were topological solitons. And topological solitons, I'll say what they are in a moment, satisfy these different requirements. Their localization, because they satisfy a nonlinear soliton equation, quantization through a topological degree, and the different winding numbers of this degree that I'll talk about give rise to different sorts of particles. So the model 1-dimensional Skermion, where we have, say, a phase on a 1-dimensional axis, is just a winding of that phase. So you have to have a phase, say, of 0, 0, 0, and then it winds around. So it wraps around the circle. We've got a mapping of the 1-dimensional line R to the 1-dimensional circle. And it satisfies a certain equation that's a soliton and so on, and that localizes the variation of the phase in this little lump, but it also wraps around the circle, and that wrapping is what we call the Skerm density. It's the Jacobian of the transformation from real space to the circle. And you integrate this quantity along the line it changes by 2 pi, winding number. And Skerm's big idea was you could generalize this construction from one dimension to any number of dimensions. So he was a mathematical physicist, but we'll see what that means concretely in real space in what's to come. So in general, if we're in n-dimensional space, so the 2D plane or 3D space, we construct a map to a sphere in that corresponding number of dimensions, but follow the same idea of using Jacobians and so on. We can wrap around that n-dimensional sphere from this n-dimensional space. And well, in Skerm's picture, with an appropriate soliton equation, we can have things that, if n equals 3, look like particles. So here's the 2-dimensional version, what some people call baby Skermions. So now in a 2-dimensional plane, the arrows live on a 2-sphere, and here's pointing up, not doing much, but in this little area here, finite localized area, they're pointing in all different directions of the sphere without discontinuities. So it's a topological mapping. And this wraps around this circle once. People call this a 2-dimensional baby Skerm. You can think about it in other ways mathematically. If we did it with the Earth, we could get all of the area of the Earth point until the South Pole within this finite area, or project from a point between us using a light between a sphere and a plane this way. So there are various different ways of doing it. The degree, what people call the degree of the map in this case, isn't a winding number, it's sort of a wrapping number. It wraps a plane around a sphere, but it's just the same idea generalized up 1 dimension. So the Jacobian now is this 2-dimensional Skerm density, where S is this unit vector on the sphere. And there's a lot of excitement in this using these ideas where these arrows are spins, for example, in magnets, because you can use these as topological bits in 1-dimensional magnetic so-called racetrack memory. So there's a lot of excitement that maybe low energy future computers can be based on computing with these topological Skermion bits, or baby Skermion bits. And some work that I did with some colleagues who were working on liquid crystals was showing that actually you can solve the heterogeneity problem, that you can get high order Skermions with what we call Skermion bags, where you put Skermions inside other ones, which tends to stabilize them. Just doing it with radially symmetric structures here, they're not stable within the nonlinear equation, but these bags are. And when we may have heard of people talking about Skermions in optics, the Skermions in optics people are talking about are versions of these optical baby Skermions. So a few years ago in science, this group talk about optical Skermion lattice, when here the direction is actually the direction of the E field in an evanescent field. That's not the only way you could do it. This group here in London, shortly afterwards, did a similar construction where now the S is the spin of the light field, and again they get a Skermionic, so baby Skermion 2-dimensional structure of their polar. Since then, several groups have observed the sort of Skermionic nature of these sorts of Poincare beam constructions. So pressing ahead now, what is it? How is this related to what I was talking about for R beams? So I'm saying we're 3-dimensional. What I was just talking about was 2-dimensional. So how do we visualize a three-sphere? That is to say, a sphere that has three angles that we'd represent in four-dimensional space. And how on earth can we talk about wrapping around three-dimensional space? How do we generalize the winding number to three dimensions? Well, as often when we're trying to go up dimensions, we can try to think what happened where in a dimension we can visualize. So what with a representation like this, you can see that actually if you start at on a regular two-sphere and go up from the bottom to the top, that's a bit like starting at the origin of the plane and moving out to infinity. So we can try a construction like that to effectively embed that three-sphere into three-dimensional space. So a three-sphere in that sense has got a regular theta and a phi angle, but then the third angle is like the tangent. The tangent of that third angle is like radius. Now, one thing, so that's one way of doing it. One thing that mathematicians have found about the three-sphere that doesn't have a lower dimensional analog is something called the Hopf vibration, which sounds very fancy, but is actually something that everybody in this virtual room knows. You just didn't know you knew. So I'm going to start with my three-dimensional space, and I'm going to cut it up. And I'm going to cut it up into circles, into filaments. So I'm going to start by having, I'm going to start by taking a straight axial line and this circle around it, just like my skeleton before, as my beginning circles. And then I'm going to say, well, this black circle corresponds to this point, and this on the sphere, this white line corresponds to this point on the sphere. Now around that, I'm going to draw tori, and I'm going to draw these loops on the torus, just as I had before, but now in an idealized way. Each circle on the torus corresponds to a point on this line of latitude on the sphere. So I have horizontal circles on the sphere. Each point on the horizontal circle is a different circle on this torus. So the torus corresponds to all these points. Each point corresponds to one of these filaments. And I'm going to keep on doing that all over the sphere. And so now each point on the sphere corresponds to a circle in this idealized three-sphere. So this is a different coordinate system of the three-sphere. It's not theta, phi, and the other angle. It's a different thing. And this representation of the three-sphere, by cutting it up into interlinked loops, is what mathematicians call the Hopf vibration. So you might say, well, you didn't know that. That's not something you've seen before. Although thinking about points on the sphere is something we're used to doing. I should just point out these Hopf vibrations have got into this Skermion world. Roger Penrose identifies this structure as what he calls a space-like twister, and what Penrose talked about as particular forms of solutions in wave equations shows up in various cases. Ivo Bielinitsky-Birula found this structure, for example, in the solution in the current of the Dirac equation in a vortex beam-like solution of the Dirac equation. These structures, which people call Hopfions because they look like the Hopf vibration, well, they occur in liquid crystal textures. This is one due to Ivan Smalyuk from Boulder. And just recently in magnetic multi-layers, where we're looking at things similar to the baby Skermions, but in three-dimensional structures. But these only involve a Hopfion. They only involve a map to the two-dimensional sphere. A Skermion really involves a map to the three-dimensional sphere, and people have found those structures in Bose-Einstein condensates, both theoretical and experimental, and in models of high-energy physics. But the experiments for the cold atoms have been very limited. Now, where does then our experiment come in, or where does optics come in? Well, the thing that we call the optical hypersphere is something that everybody uses all the time. It's just the parameter space of the normalized E field. If you think about we normalize the E field just like doing Stokes parameters. So what does that mean in terms of left-handed and right-handed components? The real part of the right-handed squared plus the imaginary part of the right-handed squared plus the real part of the left-handed squared plus the imaginary part of the left-handed squared is 1. Well, those are sum of 4 squareds equals 1. That's the equation of a sphere in 4-dimensional space. It's 4-dimensional space, real and imaginary of the right and left-handed components. What do we lose when we think about polarization is the phase. So actually these 4 components, we can parameterize a point in these 4 components, ER and EL, with, well, this thing I'm calling beta, which is related to S3, the ellipticity, the polarization azimuth, arctan S2 over S1, that's this alpha, and then what I called gamma, which is the overall phase, the phase on the ellipse, the phase of the vibration. And those 3 angles parameterize EL and ER on this 4-dimensional sphere. In fact, when we think about the Poincare sphere by ignoring the phase, what we're doing is we're taking our big 3-dimensional sphere, our sphere in 3-dimensional sphere in 4-dimensional space, and we are taking all of the states on one of those filaments with all of the different values of the phase and just identifying them with a single point. The Poincare sphere is this sphere-based space of the hot vibration of what we call the optical hypersphere. And the optical hypersphere is where you want to be if you want to think about structuring phase and polarization simultaneously. So here is just a picture. I'm going to just show you the beam again. So these are adding all of these filaments together. And this is in a slice through the x-axis, what our beam looks like. Right-handed has got a vortex line in the focal plane, vortex loop. Left-handed has got a vortex line along the axis. But what we're now doing then is we have a mapping from X, Y, Z space to this alpha, beta, gamma space. And what that means is if I've got a little cube here in real space, I can map that into my optical hypersphere 3-dimensional space, and it gets distorted. So here are the 2 filaments. They're nice and smooth in the parameter space. They're jagged in the real space. Here's a nice flat plane in the real space. It's quite jagged in the parameter space because it's based on experimental values. And in particular, then the key topological quantity is the scale factor, what people call the continuous topological charge density, the Jacobian, the size factor that takes a cube here to a cube here. On this line, this smallish cube becomes very large. The topological charge density is high. Down here, it's small. And we can do that because we've got a 3-dimensional to 3-dimensional mapping. It's a Skermion or a Skermionic Hopfion. It's not just a Hopfion because we're looking at the phase as well as the polarization. So we have this continuous Skerm density. This is the expression for it. And in terms of physical parameters, it turns out to be what people call the helicity of the orbital current. So it's quite interesting that the helicity of the orbital current is what gives rise to this topological nature of the Skermionic Hopfion. This is the experimentally measured continuous topological charge density. It should, in the model, it looks like this gold ring. It's a little bit distorted in the experiment. And this is the amount by which it fills the optical hypersphere in a volume preserving representation. Within the theory, we've got 0.945. The theoretical model is 0.997. So I'm just going to skip ahead because I see I'm running out of time. So I don't have time to tell you how we generalize to higher Skerm numbers. I'll just finish by saying the normalized optical state corresponds to a point on a hypersphere. The Poincare sphere is a base space, that hot vibration. We found and measured a structured beam which realizes almost all polarizations and phases within a finite three-dimensional propagation volume, it is a particle-like state of light. The resulting texture is, as I say, this Skermionic hopion involving polarization and phase, and it's localized not by a nonlinear soliton for us, but by beam design. It's quantized that we've measured 0.94, and it's heterogeneous. And as I say, I didn't have time to talk about that, but there's new physics that is pointing to it from looking at these structures in focused beams. So I'll leave you with this quotation from Poynting, who was talking about Kelvin's idea of knots, but it's a nice picture to leave her with as we watch the weaving of the garment of nature with these textures and filaments. We resolve it in imagination into threads of ether spangled over with beads of matter. Look closer, the beads of matter vanish. They are mere knots and loops in the threads of ether. Thank you very much for your attention.
Very much. Thank you very much for your very interesting report. Dear colleagues, your question, please.
May I ask?
Anton.
May I ask you, Mark? Morning for all. Mokhun is speaking. If you understood correctly, your consideration based on the Paraxial approximation. Yeah.
Yes.
It enough works at the far zone. Maybe it works in the Fresnel zone, but it seems me that some limitation of your approach must be. This is true? Is this true?
Well, I mean, it depends. I mean, obviously, we are choosing to work in a certain regime, and you might say we should be thinking about the three-dimensional polarization ellipse, and we could. What happens is then we don't have this three-dimensional optical hypersphere. We've actually got a six-dimensional space worrying about or five-dimensional space, EX, EY, and EZ, and then there are different topologies associated with that, but they don't quite map onto this Skermion structure, which is what we're talking about here.
I see. Thank you.
Anton, I think you've had your hand up.
Yes, I think Alberto also has a question, but I was first. Can I? Can you hear me? Hello?
Yes, go ahead.
Oh, okay. Yes, Mark, I remember a conversation with topologists and people who do topological solitons, and the question, you know, they had this jargon. This is topological, this is not topological. My understanding was that, and you also mentioned that stability of topological solitons, that Skermions can be stable. And my understanding was first that they call it topological if what they call vacuum, or when you go away to infinity and your vacuum state has it's topologically non-trivial, right? And then in nonlinear case, solitons, instabilities are nonlinear, modulation or whatever. You have linear case. My question is, what is your boundary conditions first? And second, how this topological stability works? I can imagine you mix up some additional harmonics and it's all gets destroyed or something like that. Thank you.
Yeah, so thanks, Anton. So of course, these are very important questions, and because of the having to speed up, I wasn't necessarily able to go through all of the details as carefully as I probably should have done. So the first thing to say is, yeah, so all of these states become topological because as you approach infinity, you approach the same state as So the thing that was hard for RB was to make sure that as you increase X, Y, and Z independently, you get the same state of polarization and phase. And that's what you need to make it topological. The other thing that you need, and actually it's a sort of fundamental dishonesty with absolutely all of these optical Skermion examples, is that none of them are strictly topological. If you're thinking about a quantum spin, say, it has to point in a certain direction because the only parameters that you've got are angles, because your vector is fundamentally normalized. We choose to represent this as a normalized vector. And all of these examples, whether you're talking about the direction of the spin or whether you're talking about the E vector, we're just normalizing them to pretend they actually lie on a sphere. And so, in fact, so whether you're talking about actually a linear or a nonlinear system, none of them are strictly Skermions in the actual sense of a magnet or the particle physics case.
Albert Ferrando, please, your question.
Nice to see you both.
Hi.
Again. Yes, in fact, Anton nearly stole my question because in fact this is related to the fact that as I come from, my former background is in high energy physics, and the concept of soliton was slightly different. And the role of topology as understood in quantum field theory is not exactly the same. And it's exactly what you were discussing, right? So normally, after many years in nonlinear optics, I would say that the matter is if you can have some kind of amplitude in your boundary condition, which is non-zero, so to say, which is the equivalent of going to infinity and staying in a state in which the background field is different from zero. So you have a non-trivial vacuum if you use the language of quantum field theory. Because if you work with a kind of object in which the surface, even if it's finite, and the surface sustains non-zero amplitudes field, so you have opportunity of having something with a phase but with non-zero amplitude, and this is topological. The topology means basically that you change the boundary condition, and the change of the boundary condition in terms of energy, it goes like the surface of the boundary, which means that the gap between, if you want to make a transformation, just changing the boundary condition, you require an energy which is proportional to the surface. If the surface is very big, the gap, in fact, if you go to infinity, the energy you require to transform continuously from one solution with some non-zero topology to another with another different topology, it goes to infinity. That's the standard way that you induce that you have a topological restriction, and then all your solutions have to be separated because the different topology implies different boundary condition, and this different boundary condition implies an infinite gap between the two different topological solutions. That's what basically the comment that I think it was some timely in the after Anton discussion. I don't know if you would agree with me on that.
Yeah, so obviously things are a little bit different here. So obviously it is purely linear, and I mean, I'm uncomfortable. That's one of the reasons we didn't actually call this a Skermion, because it is not strictly a topological soliton. But everybody had already started calling all of these things Skermions when really they reproduce the topology, but don't have these energetic concerns that you're saying. And as I say, what we were able to do, the thing that we had to do with beam design was make sure that we approached, in this case, this is a volume preserving representation of the hypersphere. So actually going all the way out to this surface of the sphere corresponds to the same point of polarization and phase. And the fact that within the experiment we got this close is reproducing that topology on that boundary conditions, as you're saying. But the energetics are completely different. But otherwise, I would agree with you that, as I say, but I would say whether you're in a linear or a non-linear system, none of these optical cases are strictly solitons in the way that the particle physicists talk about.
Well, I would say in some nonlinear system in which you could ensure that you have solutions which have constant density as a ground state.
Okay, but I don't know of any nonlinear optical system like that.
I think it could be
which has a where the amplitude, where the intensity is constant everywhere. That's what it would require. The intensity
could be some with proper sign, relative sign between the two nonlinearities.
Okay, it would require.
That could be a chance. You require something very strange. That I agree. But it would be possible in principle.
No, sure, it would be possible, but it's certainly far from all of the examples that people have talked about.
Okay, thank you.
Thank you. Any questions, please? No questions. Thank you for your interesting report again. The next speaker, Professor Son from Korea, thermal image for visualizing crack forming processes in
이거 왜 안 되나?
fabrics. Please.
슬라이드 쇼 클릭하세요. 이거 오른쪽 거. 네. 이거 왠지 이렇게 되네.
Hello, this is JY Son. Good morning. This is from Korea. This is now time at 5 p.m. here. And well, before I talk my just today presentation, I want to thank you to Professor Angelsky to invite me as a plenary speaker. So, as you know, the optical technology has long been used in various science and engineering as one of the key technologies in detecting, measuring, and diagnosing various physical and chemical phenomena involved with them. So thermal imaging is a very popular optical technology for diagnosing heat-related phenomena in civil and construction engineering. So my talk today is also about thermal image in visualizing the crack forming process in civil and construction engineering. So as my title of talk, the thermal images for visualizing crack forming process in mortar bricks. And
Professor Son, I'm sorry, please share your presentation.
yeah, I just put in my presentation here. I did. You cannot see?
No.
No.
You cannot see my presentation?
Yeah.
Oh,
Oh,
I did.
I believe you're sharing the browser with the Zoom connection rather than a presentation.
No, I did it. So it says now we are sharing just, yeah, it's sharing now. It said here, the green just, column, green just the color. It says I'm sharing with just my, slide here, it says. I don't understand here. Is this one? Can you hear?
Yes, okay. All okay.
Yes.
Okay, this is good. Oh, okay, this is slideshow doesn't work. Okay, yeah, anyway, so my just title of, anyway, this talk is a thermal image for visualizing crack forming process in mortar bricks. So here you can see three different technical terms called thermal image and crack forming processes in the mortar bricks. So this thermal image, I guess you are familiar with, but I don't think you are very familiar. This is a crack forming process and in mortar bricks, and these two technical terms you are not familiar, I guess. So before I talk, just get into my main subject, I wanted to explain this what is thermal image and the cracks and the mortar bricks. And I just define this one first, and I will just get into my main subject. So anyway, this work has been done with just collaboration between Korea, just Keonyang University and the Chernobyl University. So Professor Benkel, Tatiana Benkel is my just colleague in just the Chernobyl, the Ukraine University in just Ukraine. So what is thermal image? I guess you know. So thermal image, this is IR, just IR image, utilizing 1/3 wavelength range, such as here 0.9 to 1.7 micron. This is a shortwave infrared, 3 to 5 micron. You call it microwave, the midwave infrared, and Third one is 8 to 14 is a long wave infrared. So previous, we just typically we used this wavelength range, but now this all these 3 wavelengths range, there is many cameras commercially available. Just the thermal image cameras are existing here now already. So our cases, this SWIR cases, you need this signal is just so low. Also, the temperature range is very high. The typical our living environment, and this wavelength range actually requires some kind of illumination on this shortwave IR illumination. But this the MWIR and just the long wave IR, you can just use with only camera. You can have this just a very nice the thermal image you can get. So what is just the features of this thermal image? Thermal image gives both object image and object temperature distribution. So it has 2 resolutions. One resolution we called image resolution, defined by pixel resolution, and we called temperature resolution. The second one is object temperature distribution. It has a temperature resolution. So typical, well, this is a very high-end thermal camera, give just resolution, temperature resolution at 0.015 and 30 degrees. So this is just the temperature resolution, but typical. And you have just the middle end, the product, it gives about 0.03 degree at 30 degrees. So now the high-end, most high-end, the IR camera commercially available, the pixel resolution is about 1024 multiplied 768. So this is a temperature resolution here, 0.015 degrees of K. So this is well, you have to pay about 1,000 US dollars. So you can buy this camera. Actually, it's very expensive. So what is the application of thermal image? So thermal image, most applications are detect defect and abnormal symptom in various materials, such as composite welding materials and the living animal and the also human disease, such as cancer and ischemia. And it just applied, can be applied here. Also, our civil engineering department, the area, and the detection of cracks and the crack width in concrete walls, buildings, bridges, infrastructure, and detection of moisture in structures. So it's just the thermal image is used for this purpose in most construction engineering areas. So one more, just the application is observing the stress distribution of object under stress. So this is the thermal image current applications. So I explained what is a thermal image, and the next I explain what is mortar bricks. Actually, bricks represent some kind of just the prism shape, just made from actually just clays actually. But so this is just the mortar just prisms is just actually made from this concrete stuffs. We call it, instead of bricks, we call the blocks. So actually not bricks. Actually, the correct word is a mortar bricks or mortar prisms. They use this way. So what is a mortar? So mortar is a mixture of cement, sand, and water without gravel or pebbles. So this is a usual sand used here is about smaller sand particle size is about pixel size, particle size about 2 millimeter, less than 2 millimeter we use here. So what is just the mortar bricks? Block is an essential component of constructing walls of a building. So you said the previous and the infrastructure and the many bridges, many of this is some kind of essential component of constructing walls and the building everything. So this is a blocks. The most important thing, the strength of a block is actually directly related to the strength of the walls. So if you make blocks, block strength is the higher, and you can keep your walls wall strength is also higher. So the current research in the blocks data how to make the block strength is higher, and so this is the one way. So for this purpose, so to increase the strength of mortar bricks, so material with a high tensile strength, such as wire, glass fibers, or carbon fibers are added. So if you are typically tensile strength of the carbon fiber about 2.4 gigapascals, but you know the mortar brick, and this is a mortar bricks, blocks usually is set about 1.5 to 2.5 megapascal. So about this tensile strength, about is almost here, if you consider that 1,000 times higher in carbon fibers. So what is the next? What is just what is the next? What is the cracks? So crack, if you find the Cambridge dictionary, it says its definition is to break something so that it does not separate, but very thin line appears on its surface. That's what it says. So crack is just some kind of just small, just a line or a very thin line on the surface of a block. So that is actually representing and some kind of just symptom, some kind of sign or signal of just giving us a signal of just this cracks now current status. So if you just monitor the cracks on surface, so you can see, so you can understand what is the current, actually the condition of a crack, just this the blocks. You can just estimate by that. So usually, just how the cracks on the wall appears. This is usually due to contraction and expansion of walls caused by land slip, vibration, subsidence, and the settlement, heave, sway, and so on, many different reasons. So we called also in the cracks, this is a typical cracks appears, but this is not very dangerous, but we call the structural cracks. So when walls are overloaded and some kind of cracks appears in the horizontal direction, and this one, when the structural cracks appears, and this will just say the possible wall collapse. This just predict some kind of very soon the possible wall collapse will appear. So to avoid strength of a concrete wall block, the collapsing, and we have to make it the strength of this concrete wall block. We can just increase its strength. Okay, so that is the one just way to increase. So I explained before. So you add some kind of fibers or just so high tensile strength material. You put it inside of and this concrete blocks, and you can increase the strength of the blocks. So in just construction engineers, and they are monitoring the crack size up to 100 micron and above. So this is because when the crack size becomes 100 micron, some chemicals or watery component get smeared into the wall, and it just make rusting still by inside, and eventually it makes just structural cracks and eventually make it just the wall collapse. So we should monitor the cracks all the time. So this is the reason why. So we just prevent further development to the development to the structural cracks. So this region we have to monitor all the time the condition of and the walls by just monitoring cracks. So what is our goal in this paper? So we just with the use of, so for this purpose, we just with the use of a thermal image, we wanted to visualize the crack forming process in fiber-laden mortar blocks, and also possible detection of sign of signal of, or whatever you can sign or signal of a crack appearing in the blocks, and determining the time of crack onset. So when that crack appears, so we want to detect with the thermal images. So to accomplish our goals, we prepared the black samples of a size 40 millimeter by 40 millimeter by 160 millimeter. We added 5 different 5%. Just 5, this is a 5 means carbon 5%. Just 0.0. This is no 5, just added, and 0.5% in value of this black sample, and 1.0% and 1.5%, 2.0%. We added on this amount, and we made each this percentage. We have 2 samples each. We made it. So next, to measure the strength of these fibers, fiber added this mortar blocks, and which called some kind of standard procedure. We call the fractional strength test with a universal testing machine. So this one will show you later. And this universal testing machine is simply just apply some kind of stress to the blocks, sample block, and make it just break. And before the break, and the crack appears first. So by this way, and if we just measure when the crack appears on this testing on there, and if crack appears later, that means crack have a higher strength, and earlier crack has very low strength. So we can just define by time of the crack onset, and we can measure the strength of this mortar bricks. So to monitor and the test, and we use the 2 cameras. The one is a panchromatic, and another is a thermal camera. So this panchromatic camera, this is a typical visible just range camera, DSLR, okay, camera we can use. So this one is a determining crack onset time, and the thermal camera we just monitoring the signal, just the sign of crack appearing. So we to monitor, and we just used these 2 cameras, and we watch just monitoring, or we watching the just crack forming process. So we made, I already told, we have 2 samples, each just 2 samples, sample blocks for each 5%. So to identify our samples, and we just give this way. CF means carbon fiber. This is O.O dash O. So first O.O is a 5%. So I already told 0.0 or 0.5, 1.0, 1.5, 2.0. So O, the last O, the dash O is a sample number, is either 1 and 2. It is represented, right? So the strength of this mortar just blocks, we used the UTM already. This UTM is a universal testing machine. So we call this UTM. So this UTM is actually blocks, blocks and the breaking point test while applying forces just through UTM to applying forces to just the samples through UTM. And when the block have just getting some kind of a crack point. So this is just getting the crack point is just that point, and the time of getting just the crack, just crack is what we call the crack onset time. So this crack onset time actually just correspond to or equal to blocks breaking just the point actually. So it is also we can expect that the blocks with a different 5% will reveal different crack onset time. So we can see that way later. I'll show you. So our just testing device is very simple, and our experimental sample. This is a UTM called just testing the universal testing machine, and this is a black sample. This is some kind of UTM platform to set just block samples here, and this is some kind of Excel to holding and applying pulses to just this flux. And we installed about 1 meter distance. We have 2 cameras. One is the panchromatic, one is just DSLR and the panchromatic camera. This is the IR camera. Also, to just eliminate our samples, we used here some kind of lamp here. So this is the image of a panchromatic camera. So our panchromatic camera here, it has horizontal pixel resolution is about 3,800 or something, and the pixel size 6.45 micron. Number of frames, we just in video mode, it can take 24 frames per second, and the block size in horizontal direction is just 160 millimeters. So this the corresponding pixel, and this 160 millimeters here, the corresponding pixel is, if you consider this is a total just in horizontal size, camera's horizontal pixel, but actually 160 millimeters is corresponding up to this much. If you consider calculate this pixel numbers corresponding to 160 millimeter is about 3,770 pixels corresponding to 160 millimeters. So if we just consider just 1 pixel here is corresponding to about 42.5 micromillimeters. This is 42.5 just micron. So you know that if DS is just the LR camera, and if you see each image giving this kind of just informations, the frame size, total pixel numbers in horizontal and the verticals. So this is our IR image. So this IR image have just the IR. Our just IR camera has a pixel resolution 640 by 480 just pixels, and this pixel size is 17 microns. And this in video mode, it can take 30 frames per second, and the block size in this is a block size in horizontal is 160 millimeters. So this is a 160 millimeter, the corresponding pixel size, pixels, the 160 millimeter, about 628. So this 1 pixel actually corresponding to 250, about the microns. So 250, just 5 micron, here, the block size. So this IR camera is not 8 to 14 micron, but actually 7.5 to 14 microns. So this, if you just this image, you can just also find information over this image. So this is pulse waveform from the UTM, and so this is for each the samples, the just fiber edit block samples. Already I explained the 0%. There's 1% sample 1. You see the here the UTM just the pulse waveform. This pulse waveform actually you can just find. So what is the strength of this actually each just the blocks. So actually if you see that this pulse waveform and the just biggest actually the pulse here appears just requires in this for sample 1.0-1 and sample 1.0-2. So when the fiber percentage is about the 1.0%, actually it gives it just requires the highest pulse to break this just the flux. So next, if you have added more just the fibers, and they actually require the pulse to breaking pulse is down. Compared here is reduced. Also 2.0 also reduced. So they are almost the same as, and the 2.0 and the 1.5 is they are just pulse required to break the brick samples. Just is almost the same, and you can find it by this pulse waveforms. So this one gave just frame number, different frame number images we taken with just thermal camera. So this size represents some kind of pseudo color region. So this camera, this image, as you know, all this thermal camera just represent the temperature difference with the pseudo colors. So this is a temperature range 22.3 to 26.5, and you can see the as the pulse, this frame number increase means here more pulse is applied, and this is a start. Frame number is a starting time, and if you see the add more pulses, and here surface temperature increase. So this is the same, but here very uniform, almost the no fiber added, just the plain mortar the block. That's just all these surface are almost the same temperature. They're increasing very uniformly. But if you edit the fibers about 0.5%, if you see here, this is actually the this dotted rectangle area here I specified is some kind of cracks appearing when the pulse is exceeding certain amount. The cracks I specified that just cracks appearing. Okay, range. So if you just see this image, you have a white and here blue, white, blue, and here is compared with this one. Here is a blue and almost white, but here blue and the dark blue and is a white, something like that. So here temperature actual variation on this distribution. The variation is the more than these cases. So that means if you added a very small amount of fibers, and already inside, if just they just gained some kind of strength to resist the outside pulses. So you can see that from this image. So this case, just 5% is 1.0%. So if you see here, and if you keep more, also the prime number is more just increased than here, previous cases. But anyway, if you see here, and this surface temperature increasing, very much actually. If you see, also here the small just yellow just color appears. This is the highest one and appears. So eventually I'll explain it, but this is actually represent some kind of crack path. So here already saying from I guess at this point, crack is already appeared, and it is propagating more, and crack is just heated more. So when this crack is here, if you see the 1.5-2, and you can see that the symptom more. So these colors become just red, Yeah, but this red is just here pseudo color, just higher than just the yellow color. So this color is increasing. So that means, and this is a crack path, if you see, and if you see that this path here, the color distribution, and you can see here, and some kind of you can estimate by seeing this picture. So what will be the crack path? How the crack path will appear, and you can see that. And if you see here, 2.0 cases also, and you can find the crack path here. So this is a crack appears. You can just detect the crack will appear from this part already from here. It just actually just predict crack will appear from here because the temperature here is increasing. This part, this part. So this is actually crack path. So if we measure and the crack just progression time, so when the first crack appears, and we put this is we measured with just our pancreatic camera with a 1 pixel resolution, and it just gives previous I thought 42.5 microns. So this is poly just if you see the crack gap, I thought this is a corresponding to 1 pixel just the resolution here, and just 0.04 and 0.08, and with the crack gaps increasing. And once the crack just appears, after that, it just the resistance to the the crack, further progression of crack is reducing. Yeah, you see here, they are just reducing, very just with just reducing because the temperature increase is not temperature, pulse increase is very small, but they are almost flat. But there's just more just the cracks is widen, and these two just blocks is divided into two completely. So this is the means there. So this picture, and I just just specified this 12 point on the surface of this just blocks, and I measured and the temperature, time variation of temperature in surface blocks. This is a time variation of temperature on the surface blocks. So if you see that this figure, and the temperature is very uniformly increasing. All this the point, they just have almost the same way, and they are increasing. So this means they are this temperature distribution is almost the same. Even they are increased the temperature by the applying more pulses. This is a pulse just applying. If a pulse applying more and the temperature increasing, the higher, but their distribution is almost the same. The same way they are just increasing by that way. So this is another case. This is a CF 1.5-2. This is CF 2.0-2. They are increasing also the same. So what this means, the surface temperature, when you apply pulses on these bricks, the surface temperature increases. Okay, just uniformly they increase. So no problem here. So surface temperature will increase on the uniform, and this one surface temperature actually explains that way. So this is a temperature increase. You can just express by just mathematically. You can just have this is the size of a blocks, and this is the length, and this is
Professor Son, I am sorry, you have 3 minutes.
Okay. And this one that shows and crack just appearing first, and all these different samples. And if you see, this is not clearly shown, but if you see here, the crack appearance here, when the crack appears, already you can see the crack just trace here, and this is a crack is some progressed. If you can see the cracks here, and the crack appearing, so you can predict by measuring the temperature distribution. So where the crack appears on the surface of these blocks. So this is my just okay the 3 final just figures. So when just you measure the the gradient of this temperature distribution, time distribution of temperature, you can measure 0, 0, 0, 0, 2 have no just just slowly moving, and with just a small actually gradient slope. But when just you just have some kind of just fibers on there, and you can find here some kind of sudden increase the temperature gradient on this point. From this point, the temperature gradient increase, and next here also, and the temperature is increasing, and here also. This place also, the temperature gradient increasing, you can see that. So the time where this temperature, just a sudden increase, the gradient of this temperature curve, actually this one corresponding to the time of crack just the onset, just pound by our panchromatic camera. So this is summarize our actually result here on this table. And if you see here, and when does the panchromatic camera, thermal camera, the temperature, okay? So this is the ACT is abrupt, the temperature change, gradient change appears here 58.1 second, and this is a 56 point. And if you see the 86 point, 87 point. So they are almost matches. So by seeing this way, and if we measuring the temperature gradient, the sudden increase, you can find when the crack appeared. So just without any panchromatic camera, and you can see by just simply the measuring and the temperature gradient overall temperature gradient change, you can predict when crack appears, crack onset time. So this is our actually the study result. So our conclusion, and so we just showed the temperature distribution. Just the pseudo color expression temperature distribution allows the visualizing the crack forming process, and the crack path estimation also possible. The point of inflection. So this point of inflection, the sudden increase in the just the gradient of this time variation of temperature curve determines crack onset time. So actually, from that point, the gradient increase to just from just before and after that just of this this inflection point, and they just give about gradient increase up to 1.2 to 4.8 times. So we can easily and find that just the crack actually abrupt crack change point very easily here. So if we just calculate total just the difference between the inflection point and this is a crack onset time measured by panchromatic camera, and we can just find only 2.2% difference. So this is the inflection point is just temperature sudden increase, very corresponding to here, crack onset time. Well, actually, this is just my conclusions. Okay, this is all. So you have any questions here?
Thank you very much for your
Thank you.
interesting report.
Thank you. Thank you. Yeah.
Mohan, please.
Thank you very much. Mohan is speaking. As I am not expert in your area, but I have a question.
Yeah.
Practically, you fix only the outside defects. So the resolution of your method is depends on the thickness of sample and many others. And correspondingly, the temperature distribution on the surface of sample also depends on the thickness of sample and so on and so on. Is it true?
Well, I cannot say just exactly that way, because our temperature distribution is measured, okay, the fibers on the surface of that bricks. So on the crack path, okay, so I'll just show you here. If you see that this, the figures, and if you put a 2.01, if you can see here, crack appears from this crack is not continuous, and the crack just one part appearing by this way and just all the way to up, and here crack from the bottom appears this way, and there is some kind of gap. So this is what just we call the fibers and here in surface fiber. So I measured on this point, okay, and the bottom one is the this is giving some kind of abrupt change in just temperature, the time variation of the temperature curve, and this point is actually some kind of inflection, just point, and this one not just this is going slowly because this is not on the crack path. So I measured on this crack path the temperature of these fibers on this crack path. So that gives. So that means, and the thickness I don't consider very important.
Thank you.
Yeah.
Ask a question, please.
Hello.
Yeah.
Could you tell how it affects, let's say, in temperatures when it is below 0 on Celsius scale, for example? On extreme temperature, does your method works as well, or you didn't test it?
Just a second. What I didn't get it completely. So you say one more time?
So, for example, at least from the presentation, I saw that you used your method in normal temperatures, like 25
yes, our room
degrees
temperature.
Celsius.
Yeah.
Yes, room
Well, yeah,
temperature.
this is yes, Celsius.
How it works with extreme temperatures, like below zero, like hot temperature and so on?
Well, you know, this we used, and this well, our laboratory is inside just the buildings. So actually, just inside the room. So its temperature cannot be below than just actually 20 degrees. So I just show you here the temperature. So here, just the minimum temperature 22.1 degrees here. So I consider if just even if a temperature this is a 0 degree, I still this if you apply just pulses here, this flux will be heated. So this is what it shows, here. So this is a 22.1 to 26.5. Of course, if you have outside, the very low temperature, they're losing some heat. So maybe this is just increasing. The temperature increasing will be low, but still you can find, because this is a camera, you have 0.03 degree and the temperature resolutions. So it still gives some kind of a temperature distribution increase. So, and not this kind of, and very bright temperature distribution, but maybe if you're very low temperature, this kind of distributions, or this kind of distribution, well, this we can still find actually, and at this point we can find some kind of a temperature gradient. So we can still find actually the breaking point. So crack onset time, we can just very accurately we can determine. Yeah.
Okay, thank you.
Yeah.
Other questions?
Yeah.
Question is absent. Thank you.
Thank you. Thank you very much.
To you
Thank you.
again. To you again.
Yeah. See you again.
The
Of course.
next-
Yeah. See you then. Yeah.
Thank you. The next speaker, Professor Bloch from Japan, a new spin for acoustics. Please.
Hello, everyone. Yeah, can you hear me? Oleg, can you hear me?
Yes. Yes.
Okay, perfect. Thank you very much for inviting me here. Hopefully, in 2 years, we can participate in offline correlation optics because Chernivtsi is a beautiful city to visit. And this time, I'm speaking from Ukraine, Kyiv, and I would like to share my presentation. Let me do this. Okay, can you see my presentation? Okay, perfect. So here I would like to overview our recent works in the field of acoustics, but these works have a lot to do with optics and traditional area where I worked so far. And this is about spin, momentum, angular momentum, and so on. So therefore, I will start with a comparison between electromagnetism and acoustics. As you know, there are two basic types of waves in nature. These are transverse waves, where the displacement of particles or fields are orthogonal to the wave propagation direction, that is to the wave vector. And these are longitudinal waves, where the displacement of particles or wave fields are collinear with the wave propagation direction. For instance, electromagnetic waves are transverse, and acoustic or sound waves in fluids or gases, these are purely longitudinal waves. Okay, and it's often believed that sound waves are scalar, while this is not exactly true. They're vector, they're longitudinal but vector waves. Because there is a displacement vector in sound wave. For instance, particles are displaced, you can measure it by the displacement or velocity, and this is a vector quantity, not a scalar one. And if we write down equation of electromagnetism and equation for acoustics, they look very similar, and there is a very nice correspondence between these two. For Maxwell equations, of course, you know that we have two vector fields, electric and magnetic, and two medium parameters, permittivity, epsilon, permeability, mu. And essentially the same happens for acoustics. sound wave field is described by two fields, velocity of the particles and pressure. And the difference is that pressure is a scalar field. So we have one vector and one scalar field. We have two parameters of the medium. Rho is the mass density and beta is the compressibility of the medium. And also we have transversality condition for electromagnetism and longitudinality condition for acoustics. So curl of the velocity field must vanish. If we write down the main conserved quantity, the energy density and the kind of Poynting vector or kinetic momentum density, they also look very similar in electromagnetism and acoustics and very symmetric quadratic forms of the two fields in both cases. And therefore, we can expect that there could be nice analogies between electromagnetism and acoustics. So the main dynamical quantities which describe any wave field are momentum and spin. And momentum is associated with the wave vector or phase gradient in the field, while spin is produced by the rotation of the vector of the field. So here I show that gradient of phase is proportional to what we call canonical momentum density, and it can be written as this quadratic form. For a vector field F also, Mark showed a similar form in his talk today's morning. And if we are interested in the local angular momentum of this field, of course, it should be proportional to the rotational characteristic of this field, and it's given by this this vector form F star cross F imaginary part. So this is proportional to the ellipticity of the polarization and directed normally to this polarization ellipse. Okay, so for plain electromagnetic wave, we have a well-known picture. Momentum is aligned with the propagation direction, and if the wave is circularly or elliptically polarized, there is a spin which is also directed along the momentum or in the opposite direction. For single sound plane wave, the situation becomes trivial because velocity vector must be aligned with the k vector, and therefore it has only 1 degree of freedom. It's linearly polarized, obviously, and there is no spin, there is no rotation. And that's why we say that photons are spin 1 particles, while phonons are spin 0 particles. However, if we consider generic structured and homogeneous wave fields, such as the interference of many plane waves, there is no local correlation between the phase gradient or momentum and the field direction or spin. And both electromagnetic and sound waves are generally elliptically polarized in any given point. So here it's an arbitrary example of interference of random wave fields. And you see we have some structured distribution of polarization ellipses. And this happens both in electromagnetic and acoustic waves. I would like to emphasize that in the case of sound waves, these polarization ellipses, these are ellipses of the velocity field or displacement field, and they correspond to real space trajectories of particles of the medium. For instance, if we hear sound in the air, molecules of the air move along such ellipses in real space. Okay. So the simplest example, if we interfere two plane waves, this generates in homogeneous pattern, periodic pattern of the momentum density and spin density distribution. So here I show an example of interference of two electromagnetic waves and K1, K2. The wave vectors E1 and E2 are corresponding linearly polarized electric fields. Each of these is orthogonal to its corresponding K vector. And the result is shown here. So the black arrows show the canonical momentum density, and the color distribution shows the spin density directed in the orthogonally to this plane. So we have periodic transverse spin. Now, if we interfere two sound waves with the same angle between them, and I now show velocity fields, and now each of the velocity fields is collinear with its K vector. So the field at each plane wave is longitudinal. but the interference is exactly the same because you interfere linear superposition of two linear oscillations in orthogonal directions. Okay, so we again have similar canonical momentum and similar periodic spin distribution in the transverse direction. And this exactly was observed in a recent experiment, 2019, in this group by Jiren in China. They actually introduced this concept of acoustic spin and measured spin density in the interference of two orthogonal sound waves. They measured torque on a kind of absorbing structure. They called it meta-atom, but it's quite macroscopic. And the results are in agreement with theoretical predictions. And in a similar way, evanescent waves, both electromagnetic and acoustic, possess a non-zero transverse spin. Here I show you the transverse character of a plane wave and longitudinal character of plane wave for sound waves. But if you take a complex k vector as for evanescent waves, so you have real part of k for the propagation and imaginary part of k for the evanescent decay, then in these cases, transversality condition for electromagnetic wave and longitudinality condition for sound waves results in an elliptical polarization in this propagation plane and the corresponding transverse spin as shown here. Okay, so simplest analog of the transverse spin is the rotation of water particles in surface ocean waves, as shown in this animation. As you know, water waves propagate along the surface, and the particles of water move along circular or generally elliptical trajectory. This is the transverse spin. And the same happens in the sound waves, and this was observed in the same paper for acoustic spin. And this transverse spin has the property of spin momentum locking. So depending on the direction of rotation of these molecules near the surface, the wave propagates in the right or left hand direction. So they observe the spin momentum locking for acoustic waves. Okay. So then how do we mathematically describe spin and momentum for sound waves? And we use essentially the same fundamental construction as for electromagnetism. This is so-called Behlin-Fanter-Rosenfeld decomposition of the Poynting or kinetic momentum density. It can be, this is known from field theory for a long time, so that kinetic momentum density Poynting vector can be decomposed into canonical momentum and half of the curl of spin density. So for electromagnetism, this yields this well-known expression for the canonical optical momentum and spin densities. And if we do the same procedure for sound waves, we derive very similar and very nice formulas. This is canonical momentum given by the same form and the vector velocity field. And this is the spin density given again by a similar form for the same velocity field. But what is the important difference is that in contrast to electromagnetic fields, acoustic waves exist only in a medium, and therefore they're intimately related to the motion of the medium particles. And therefore we can associate the wave properties with the mechanical properties of the medium particles. So first, as I mentioned, particles in the medium, for instance, in the air, in the sound wave field, generally move along elliptical trajectories if we assume monochromatic waves. And then we can write the displacement field, complex displacement field, and complex velocity field. They're, of course, related to a time derivative. And if we calculate the time averaged angular momentum density for these rotating particles of the medium, which is given by cross product of A and V, multiplied by the mass density, we obtain exactly the spin angular momentum density in sound waves. So therefore, the sound wave spin is the local mechanical angular momentum of the medium particles. Important for sound waves, localized sound waves, for instance, wave packets in a homogeneous medium, integral of this spin density always vanishes, which again corresponds to the spin zero property of phonons, of sound phonons. But local spin density is generally non-zero. Okay. So then, as we know from hydrodynamics, the motion of the medium particles allows the Eulerian and Lagrangian description with the different coordinates following particular particle or attached to the particular point in space. And the difference between these coordinates is given by the integral of the velocity field or to the by the displacement vector. And then if we calculate time average difference between the Lagrangian and Eulerian velocities, there is a quadratic correction. So velocity, Eulerian and Lagrangian velocity differ by a quadratic term. And this quadratic term is known as the Stokes drift in fluid mechanics. And for longitudinal waves, this Stokes drift is exactly proportional to the density of the canonical momentum I showed you before. We just need to multiply by a mass density ρ. And therefore, the canonical momentum of sound waves is exactly associated with the Stokes drift of the medium particles. So here are some animations from Wikipedia. So you can see how, again, the same example of surface ocean waves. And you see that in addition to circular motion of water particles, they slowly drift in the direction of the wave propagation. And this is the Stokes drift. And actually, it has a lot of consequences because it's responsible for the mass transport, such as this wood drift on the ocean coasts. Okay. So to summarize, we have a clear mechanical explanation of the acoustic spin and momentum densities. Now, a direct way to measure momentum and spin densities is to put a probe particle and to measure radiation force and radiation torque on this particle. This is how we typically do in optics. And in optics, for small subwavelength particle, the main coupling terms are electric dipole interaction and magnetic dipole interaction. And correspondingly, if we describe this interaction by the electric and magnetic polarizabilities of the particle, we know a general expression for the scattering force, for the torque, and for the gradient force. And these are proportional to the electric and magnetic parts of the canonical momentum, canonical spin, and energy density in an electromagnetic field. If we do the same calculation for sound waves, we put again a small subwavelength particle. The main interaction terms between the particle and the wave field are the monopole coupling and the dipole coupling. And the monopole couples to the scalar pressure field, and the dipole couples to the vector velocity field. Generally, these couplings have, this interaction have the same order of magnitude, and we can derive scattering gradient forces and torque on the particle. And they, again, nicely proportional to the canonical momentum, spin density, and parts of the energy density for sound waves. Okay. So then we can further proceed with this analogy. In optical fields, we can combine electric and magnetic dipoles to generate circular or Huygens or Janus dipoles. This was described a few years ago by Michela Picardi and Paco Rodriguez Fortunio. And combining these dipoles, you can have a very nice directional couplings as shown in these pictures on the left. Combining different dipoles, you can couple to the right propagating, left propagating waves, upper surface waves, lower surface waves, waveguide, and so on. The same essentially can be done with sound waves. You just need to combine the monopole and dipole coupling terms for the particle, which can be controlled by the properties of the particle. And you can do the same nice directional couplings. Okay. Now, I would like to discuss water waves. So far, we used water waves only for analogy with acoustic waves, but now let's consider them explicitly. And we will use deep water approximation. So these waves are called gravity waves on the water surface. And since these are surface waves, we consider them as a quasi-2D system, wave field. And therefore, we separate velocity of the water particle into two-component vector capital V, which is X and Y components of the velocity, and W, which is the Z component of the velocity field. So let's consider them as two different fields, okay? And we will be interested in the two-dimensional momentum of the wave in the plane of propagation and in the vertical spin, which is orthogonal to this plane. And then using the same Stokes drift arguments and angular momentum arguments for the rotation of water particles, we can derive canonical momentum and spin density in monochromatic water surface waves. And they look very similar to the acoustic ones. Here we have two terms related to the in-plane surface velocity and vertical velocity, and spin is determined only by the in-plane velocity. And if we substitute this canonical momentum and spin into the general field theory, Belinfante-Rosenfeld relation, we can derive the kinetic pointing-like momentum of surface waves, which looks very compact and nice, but surprisingly, it's very non-trivial result. It's typically not known in the fluid mechanics community. It was derived only in 2010 by the American mathematician Peskin. Okay. And in contrast to acoustic waves, where the motion of particles is happens in real space, but it's really tiny. It's very difficult to observe it directly. With water waves, we can directly observe without any microscope how particles move in complex wave fields. And therefore, in collaboration with Michael Schatz's group in Canberra, Australia, we performed a nice experiment in the hydrodynamical laboratory. So they interfered two or more plane water waves in the wave tank using these shakers and pedals. Each of them excites a single plane wave, propagating orthogonally to the pedal. So it's easy to create a two-wave interference and observe the motion of the water particles. So here I show on the left theoretical prediction for the canonical momentum and spin density, which I showed before. Then numerical calculations of the water particle trajectories, which we expect in this system. And finally, the direct experimental measurements of how water particles move. And we exactly observe rotational motion, right hand or left hand, according to the spin distribution. And we exactly observe Stokes drift in agreement with the picture of the canonical momentum density distribution. This is a similar experiment for 4 interfering plane waves or two interfering standing waves. They generate such a periodic array of vortices, macroscopic vortices in water, and macroscopic vertical motion corresponds to the Stokes drift, which generates now orbital trajectories, while local circular motion of water particles corresponds to the spin density, again in full agreement with theory. Okay, if I have some more minutes, I would like to show you now some other recent results. So the main point is that we can explore and employ polarization properties of sound waves essentially in the same way as in electromagnetism. And they have essentially the same richness and the same potential for different complex structures as in electromagnetism. For instance, in this work made recently with Miguel Alonso and Etienne Brasselet, we explored polarization Möbius strips and polarization singularities in interfering acoustic or surface water waves. And here we show pictures for interference of several water waves and elliptical trajectories of water particles in each point. And black dots are C points of this polarization distribution, and around C points, as in electromagnetism, you can observe polarization Möbius strip generically. So this is all these simulations and pictures were done by Danica Sujic, and let me show you the animation. This is real interference of several water waves with the same frequency, and you see how particles on the water surface move. You see polarization ellipses, and in this picture around the sea point, you see that polarization ellipses or particle trajectories form a Möbius strip if you follow the major semi-axis, local major semi-axis of these ellipses. Okay, and another work done with Danica Sujic and Mark Dennis, we considered interference of 3 or more vector waves with different commensurable frequencies. And similar to Lissajous polarization described by Isaac Front long time ago, in 3 dimensions, you can generate different types of knots. And so vector field, its polarization follows a knotted trajectory in the field space. Okay, and again, a very visually appealing example, if you interfere several water waves with different frequencies. In this example, this was, I think, 3 or something like this wave. And you can see how water surface particles move along knotted trajectories. There could be many different types of knots. Okay, so to conclude, there is a profound analogy between the dynamical properties of electromagnetic and acoustic waves. Sound waves are longitudinal, as we know, but they're still vector waves. They generally possess non-zero spin and canonical momentum densities, and acoustic spin is produced by the local rotational motion of the medium particles, while canonical momentum is associated with the Stokes drift of the particles. Similar to optics, acoustic momentum and spin exert radiation forces and torques, and then electromagnetic and magnetic dipoles in optics correspond to acoustic monopole and dipole interactions. And finally, water waves also have similar properties. We have directly observed the particle motion underlying the spin and canonical momentum densities. So this is a concluding table where I compare the basic dynamical properties of electromagnetic, acoustic, and water waves, including Poynting vector, canonical momentum density, and spin density. And you see there is a very nice correspondence, also differences, but they all satisfy the same fundamental Belinfante-Rosenfeld relation from field theory. Thank you very much for your attention.
Konstantin, thank you very much for very interesting report. Your question, please, colleagues. Mohun, please.
Thank you very much. Kostya, добрый день. Yeah, I have a question. Maybe it does not concern to the title, but can you construct the acoustic or water field which is completely similar to the speckle field?
Yeah, random interference will be a speckle field. Why not?
Why not? And correspondingly, all topological regularities are worked here. Is it true?
Well, depends what you mean by topological. You mean for singularities?
Yes, for example, sign principle and so on.
I think so, yes.
Yes, thank you very much.
Welcome.
Professor Albert Ferrando, please.
Albert?
Yes. Hello, Kostya. Nice to see you. Yeah,
I can see you.
Very much for your very interesting question as usual, talk as usual. I'm wondering, since you are talking about this new degree of freedom or the analogous degree of freedom in acoustic wave as compared to electromagnetic waves, I was wondering if this would affect the usual coupling between photons and phonons in the standard way, because you know it's very common in condensed matter physics to consider at the quantum level interaction between acoustic phonons and photons. Of course, this is a classical approach, but since it's linear, I would expect that some kind of effect could be also observed somehow in this kind of experiments. And I think if you think about it, because you haven't talk about the mixing of these two, but probably you are going in that direction as well.
Yeah, thank you. This is a nice question. Probably yes, because in all this interaction from high energy to interaction in condensed matter between different types of particles, people mostly consider something like plane wave interaction. You have incoming K vector and outcoming K vectors, like scattering problem. For plane waves, everything is trivial. But if you consider some interaction which involves structured waves and structured states, for instance, instead of Gaussian wave packet, you have Laguerre-Gaussian wave packet and their interaction and scattering, then these degrees of freedom could play a role. So
that opens a very interesting line of research.
This should be a very interesting direction, but also all phenomena should be very fine and really related to fine subwavelength structure, something like this. As soon as you are talking about local interaction involving nanostructured, subwavelength structured waves, then all these degrees of freedom come to play, right?
Okay. Thank you very much.
Professor Mark Dennis, please, your question.
Hi, so Kostya, thanks. It's very interesting to see it all of these various things over the years come together. So what your sort of presentation made me think is that this use of spin, which we use as a way of describing multi-component objects, which is really very useful. And of course, in the textbooks is always plane wave. Your point is that actually it's not what it says for plane waves. It's exactly what we always do just for transverse waves. They look like spin half, and obviously they're spin one. So the question really is, do you think we should be moving away from this description of spin, or modifying our description of spin when we're thinking about structured waves? Should we be adopting a different formalism and use that, for example, if we want to go to tensor waves, which will be the next stage, for example, in elasticity or something? Well,
why I'm not comfortable with the spin description? So spin is angular momentum characteristic, right? That's why.
Right. So I guess what I'm meaning is if you're talking about your acoustic waves, are they scalar spin 0? Are they spin 1? I mean, what you're saying is there's elements of each depending upon what you're actually doing.
No, I didn't say it's there are elements of spin 1. I just say that integral spin is 0, so they're really spin 0 waves. But the local spin density could be non-zero. This is the point. Integral spin wave, okay, but
so the question, so as I say, so the question is it sounds like there's another formalism that we should be using, which isn't just spin. If we're you can fill out the sort of elements of the table, and maybe there are more pieces of the table that for other systems.
I think you're right. So particularly from the mathematical point of view, in terms of equations, you can find different structures corresponding to, like you found Skermion structure naturally appearing in paraxial light. So we never thought about this before, right? And you found the structure which is kind of inherent in this description, right? So probably here in acoustics you can do the same. So different. In particular for elastic waves, where you have both longitudinal and transverse waves, the structures could be really complicated. What is good, what I like about spin description is that it corresponds to angular momentum, which is physical dynamical property directly measurable, and that's why I like it.
Okay, so maybe what we should do is use spin, but spin is not intrinsic in quite the same way. You have to look at the expressions that you're seeing and seeing how it manifests as angular momentum. Ultimately, I guess related to Alberto's question before that, and seeing how it deals with interactions. Okay,
probably I would say this, that in classical physics, for classical waves, we use spin in a slightly different manner as compared to for instance, quantum theoretical physics, right? It's not related to statistics like fermionic or bosonic. It's mostly related to classical angular momentum, and in this case, in our case, mechanical properties of these waves, right?
Right. Okay. Thank you.
Thank you, Mark.
Thank you. Any questions? Question is absent. Thank you all the participants of this section, and the next plenary session will start at 2 p.m. See you later. Bye-bye.